Hey everybody, Dr. O here, and I thought I'd make a little video going into factors that affect blood flow. So first of all, what is blood flow? Well, blood flow is the amount of blood flowing through a vessel or an organ or even the entire circulation in a given period of time. So it's actually volume over time, and it's measured in milliliters per minute. And we can actually equate it to cardiac output for the entire vascular system. Now, normally our blood flow is going to be pretty constant, mostly when we're at rest, but whenever you get up and move around and the demands of the body alter a little bit, it's going to vary. Throughout the body, and depending upon which organs are more active, then blood flow is going to alter within those organs. Some organs may get a little more, like if you're running a marathon, your muscles are going to get more blood flow, but your stomach isn't going to get as much. So things can shift around depending upon what the body's need is. But for the most part, blood flow is this certain amount of blood moving through an area in a given period of time. Now, when we talk about blood flow, an important aspect of blood flow is blood pressure. So what is blood pressure? Well, blood pressure is the force exerted on the wall of a blood vessel by the blood moving through it. And we express this in millimeters of mercury, and it's measured as a systemic arterial pressure, mostly in our large vessels that are near the heart, where we can actually capture the pressure of that blood as it first enters into systemic circulation. Now, there's a pressure gradient that gets established in the arterial side, well, actually all the way through, but largely um, we'll see most of the pressure in the arterial side of systemic circulation, and it starts to taper off in the venous side of circulation. So this pressure gradient is what provides the driving force that keeps blood moving from areas of high pressure to areas of low pressure. So blood starts out at about 120 millimeters of mercury as it enters into the aorta, and then it starts to lose some of that kinetic energy as it moves its way through the systemic vasculature until by the time it returns to the heart, it doesn't really have any pressure at all. So that's the concentration gradient we're talking about. When we talk about flow, an important consideration is something known as resistance. And resistance is going to be something that opposes the flow of blood. Now, this is going to be basically a measurement of something that's creating friction within a blood vessel, and it's going to be things like the vessel walls, and that's probably our greatest one. But there are some other factors that we can look at as well, and there are three important uh, sources or factors that lead to resistance. One of them is the blood viscosity, and we'll talk about that in just a second. The total length of a blood vessel, that plays a role, as does the blood vessel diameter. So let's take a look at each one of those. Now, I said a moment ago that blood viscosity is really the stickiness or the thickness of the blood. So when blood is sticky, that means that the red blood cells have a tendency to want to stick to each other, and that's going to create resistance to flow. They just don't tend to roll along in that blood vessel as easily as they could otherwise if they didn't have a great deal of viscosity to them. So if you have blood that has an increased number of red blood cells in it, it has a tendency to be a greater viscosity than blood that has a normal amount of red blood cells in it. And there are conditions where this can happen in the body, where the body will be triggered to make too many red blood cells. And that becomes a problem for the person who has that condition. So however thick your blood is, that can play a role in creating resistance to blood flow. Now the other one is the total length of the blood vessel. And with this, what's really happening here is that when the blood makes contact with the vessel wall, that creates a resistance as well, because blood's going to want to stick to the vessel wall. So the fact that blood wants to stick to the vessel wall slows down the flow, and that is another form of resistance. And if you're traveling over a short vessel, well, then that's not going to be that big of a deal. This length of the blood vessel is not going to contribute that much to resistance. But if you have a really long blood vessel, like one that's going to go all the way down down your leg to your toe, well, then that blood that's in that vessel is going to have more vessel to travel through, which means that blood has more time to be exposed to that vessel wall and will experience greater friction in its travels. Now, of the three that we've talked about, blood vessel diameter is going to have the greatest influence on resistance. Now, why is that? Well, it's because blood vessels can actually change their diameter and create this resistance. That's why. Whereas if we were to look at viscosity of our blood, that doesn't really change from moment to moment. Now, if you have a pathology and you have issues there, then yeah, over time you can see an increase in blood viscosity, but it really doesn't change for most people. And so viscosity won't be as big of a contributor. It contributes some, but not as much. And blood vessel length doesn't change from moment to moment either. So viscosity and blood vessel length are pretty stable. So it actually ends up being the alterations that we see in blood vessel diameter that play the biggest role in creating resistance to blood flow. So as I said a moment ago when we were talking about vessel length, the fluid that is close to the walls of the blood vessel is going to be moving more slowly, and it's because it's encountering friction with that vessel wall. And so the blood that's next to the vessel wall moves more slowly. Meanwhile, the blood that's in the middle of that blood moving through a vessel is going to be moving a little bit more quickly. And what we see as we look at the blood going from the center of a vessel all the way to the vessel walls is that the closer the blood gets to the vessel wall, the slower it goes. The more the blood is towards the middle of a vessel, the faster it goes. And this is what we call laminar flow. Laminar. So lamina are like layers. And so we could actually think of the blood moving through a vessel being in layers where you have a center layer and then a layer outside of that and then a layer outside of that, very much like rings on a tree. And the further you get away from the middle, the slower the blood is going to flow. Now, when we look at resistance in a blood vessel, the thing that we can say is that the resistance in a blood vessel is going to vary inversely to the fourth power of the vessel radius. So what is the short version of that? Well, basically it means that if our radius increases, resistance is going to decrease. Or if radius decreases, the resistance is going to increase. So let's just look at a little example. So let's say that we have a relatively small blood vessel here and we're going to fill it with a certain amount of blood. What we can notice is that there's a lot of this blood that's making contact with the vessel wall. And we know that when blood is making contact with vessel walls, it's going to create resistance. So in a scenario like this, where we're trying to move a certain amount of blood through a small diameter vessel, we're going to have a small diameter, which is going to create a great deal of resistance to the flow of that blood moving through that vessel. Now, what if we took a larger diameter vessel and we tried to move that same amount of blood through it? Well, we might end up looking at something like this, where now most of our blood is actually kind of in the center. Very little of it is making contact with the vessel wall. So in this case, we're going to have a large diameter, and conversely, we're going to have a small resistance. Now, in reality, we're never going to be moving the same amount of blood through a large vessel that we would through a small vessel. If a vessel is large enough, then the body's going to fill it with blood. But even in that scenario where a large vessel is filled with blood, there's still more blood in the center of that large diameter vessel, relatively speaking, looking at the ratios, than there would be blood in the center of a small diameter blood vessel. So the large vessel just inherently doesn't have as much resistance as a result of that large diameter. Now, when we look at the arteries in the body, we have the largest artery attached to the left ventricle, and that's called the aorta. And then as the aorta travels around, there's going to be branches of arteries coming off of that, and every branch is smaller than the aorta. And in fact, every branch is smaller than the branch that it branched from. So we get smaller and smaller arteries until we get really small arteries that are called arterioles. And then arterioles are the smallest vessels that are ultimately going to lead into the the tiniest of our blood vessels, which are called capillaries. Now, we can get some of the intermediate size blood vessels to do a little contraction, and it's not going to have that big of effect on blood flow. But when we have an arterial, which is an already small diameter vessel, doing contraction, constriction, and dilation, that's going to have a major impact on peripheral blood flow resistance, or resistance to blood flow. I guess that's a better way to say that. And these are the vessels that are going to change diameter the most. These vessels are largely responsible for moving blood around the body and ensuring that organs that are having a high demand moment get the blood when they need it. So the radius of these vessels is going to change a lot. We don't really see that happening so much in our larger diameter vessels, and it's just the nature of the vasculature. And so that's one thing that's going to contribute tremendously to resistance. Another thing that can contribute to resistance is an abrupt change within the structure of the vessel. So maybe something like a plaque buildup inside of an arterial, that can create a lot of problems to that laminar flow that we're expecting to see. It acts like a speed bump and creates turbulence. So just like a speed bump is put in a road to slow down traffic, a little fatty plaque acts like a speed bump and slows down our blood. Maybe something we don't really want. Probably not something we want at all. So there's a couple of things in these small vessels that can create resistance. First of all, the vessel itself, and then if there's any alterations to the vessel wall, that too will create a disturbance and an increased resistance to blood flow. Now, there was this Frenchman by the name of Poiseuille who came up with the formula that tells us about the relationship between pressure and radius and the viscosity of blood, as well as the length of the blood vessel. And he was able to put all this in a very complicated equation and to describe blood flow. Good news for us is that although it's here on the slide and you get to see a peek at what all went into that, we don't have to do any math with this. We just need to understand the relationship between blood flow, blood pressure, and resistance. So let's do that. So when we look at the equation that Poiseuille gave us, which is right here down here, we've got flow is equal to a change in pressure over resistance. So what we can say then is that blood flow is going to be directly proportional to blood pressure, so that if pressure increases, blood flow speeds up. We can also say that blood flow is inversely proportional to peripheral resistance, which means that if resistance increases, then blood flow would decrease. I know this is a lot of words. Let's look at it a different way. So the first thing we can look at is the relationship between blood flow and resistance. So it says here that blood flow is inversely proportional to resistance. So what does that mean? Well, it means that if our resistance goes up, our flow is going to go down. It also means that if our resistance goes down, our flow is going to go up. That's the relationship between the resistance and blood flow, because we know that resistance is going to oppose flow. So when resistance goes up, the flow goes down, and vice versa. So thumbs in opposite directions. So here we're going to talk about the relationship between flow and pressure. And what we know is that it is a proportional relationship, which means that when pressure goes up, so does flow. And conversely, when pressure goes down, so does flow. So this is thumbs in the same direction. And hopefully that makes some intuitive sense. So that if you had more pressure pushing fluid through a hose, it would have a tendency to want to come out at a faster rate. Now, a moment ago, we talked a little bit about turbulence, and we also talked a little bit about normal blood flow in a healthy vessel. And the thing that we can say about healthy blood flow is that it's going to flow in one direction in that vessel. The blood's going to flow in one direction. So if we bring up a blood vessel and we put in our laminar flow, so this is flowing kind of slow, and then the blood next to it's going a little faster, and the blood down the center is going the fastest. But you can see by the arrows that we're trying to indicate that all the blood is going in a single direction. Everybody's moving along the best they can, having to deal with things like viscosity and the friction against the vessel wall, and maybe even the vessel wall diameter and the length. So the usual things that we think about when we think about blood flow. But when you have a scenario where you end up with a damaged vessel or a clogged blood vessel or a little plaque buildup in that wall, something going on like that, something that can disrupt this normal flow, then you create these swirling patterns in the blood vessel, which means that blood's going to flow until it hits that little bump, and then it's going to cause it to flow backwards, which is going to impede the blood flowing in back of it, and then it's got to get straightened out and figure out which way is forward, and then start moving forward again where it might hit another bump and then create another swirling pattern and create more resistance, and then here you are with this very bad situation because these swirling patterns are creating additional resistance in that blood vessel. And of course, that's going to put stress on the cardiovascular system, including our buddy, the heart. Now, through all of this, we've talked about the flow of blood, but we never really talked about where blood gets the energy to move. Well, systemic blood is going to get its energy from that left ventricle. So that very powerful left ventricle is what is forcing blood into this pressurized system and helping create that concentration gradient. So yes, our blood pressure is going to be the greatest near the heart and is going to lose its pressure as it moves throughout the vascular system, particularly in the systemic circulation. We're going to see pressure drop the longer that blood is in systemic circulation, until by the time it returns to the heart, it's really under hardly any pressure at all. So blood flow is going to be proportional to the pressure gradient. And systemic pressure is going to be the highest in the aorta, and we lose that pressure. Like I said, that kinetic energy gets dissipated as the blood moves through the entire vasculature. And believe it or not, the greatest drop that we're going to see isn't in the tiniest of our blood vessels. It's actually in the arterioles. And it's because our arterioles can create the greatest resistance in peripheral systemic blood flow. And with that, we are done with this little tour of blood flow, blood pressure, and resistance.